I'm Clay Morrison, and this is my Lab 4 lab report. So the purpose of this lab was to use Kirchhoff's rules, Ohm's law, and an online circuit simulator to predict the behavior of ohmic resistors, capacitors, and circuits that contain resistors in both series and parallel orientations. And then, in addition, we're going to determine the conventional current and potential difference values in these circuits. So the physical principles used, first of all, were Kirchhoff's rules, which the first rule that was used was the node rule, which is the same as the conservation of charge principle, and it states that the sum of all currents entering a junction must be equal to the sum of all currents leaving the junction. And then, secondly, the loop rule, which is the same as the conservation of energy principle, and it states that the sum of changes in potential around any closed circuit path must be equal to zero. And then finally, we used Ohm's law, which states that the current is equal to the voltage over the resistance. So for part one of the experiment, we had to orient a circuit as shown here and calculate the predicted current, which is done using Ohm's law, voltage over resistance, 3 volts from the 1.5 volt batteries, and then 147 ohms from the combined resistors over here. And then we had to replace one of the ammeters with a voltmeter. So the ammeter that was remained displays 0 amperes because the circuit's now open from the voltmeter, and there's consequently no current flowing through the circuit. And the voltmeter reads -3, but that's just because of the orientation I had it in. So taking the absolute value of that, it's 3 volts, which is the same as the potential difference between the two batteries. So going around and taking the potential difference measurements between the points as specified here, I got these values on the left, and summing them equals 0 volts as it should, because it agrees with Kirchhoff's loop rule as stated a few slides ago. So building this graph right here, basically it's potential versus position around the circuit, and the electric field is equal to the negative gradient of potential. So these spots right here have a large E field where there's a change in potential, and then where there's no change right here, it doesn't have an E field. So calculating the resistance, again using Ohm's law, at the specified points here, using voltage over current, I got 47.95 for the 47 ohm resistor, and 102.05 for the 100 ohm resistor. And then the resistance in the wire is equal to the resistance in the ammeter at 0 ohms because it's just a theoretical computer model, and they don't have any resistance. So when an ammeter is added in parallel orientation to the circuit, both ammeters read 0.06 amperes because the current splits between the junction as it should according to the node rule. And then getting into part two here, so setting up the circuit with a capacitor here, a battery here, and a bulb here, the light dimmed when the capacitor was charging, and it turned off completely when the capacitor was completely charged. And this is because the current moves increasingly slower through the circuit as the capacitor is being charged until it eventually comes to the stop. And so basically the same thing happened when I discharged the capacitor, and just because it still moves increasingly slower until eventually stopping, but it moves in the opposite direction while the capacitor is being discharged. So continuing part two here, for the 10 ohm bulb, I found that using a stopwatch, I found that the charge time was 10.34 seconds and the discharge time was 10.46 seconds. And then for the 20 ohm bulb, the charge time was 21.03 seconds and the discharge time was 20.87 seconds. And then the theoretical RC time constant is just 0.2 farads times 30 ohms, which equals 6 seconds. And then my experimental value I got from the slope of the graph of L and V over V naught versus time. And I set it equal to -1 over RC, given the specified equation. And I got RC equals 6.79 seconds, which is relatively close to the theoretical value of 6 seconds. So getting into the conclusion questions here, if I were doing this lab in real life and using an actual ammeter instead of a computer model, a real ammeter would have provided additional resistance and consequently would have decreased the current values, and increase the potential values, and that can be inferred using the Ohm's law equation. And if I were doing this lab in real life and use a real battery to charge a capacitor with no resistor, um, and how would it, basically it's asking how would it vary from the computer model, and the computer model would predict the capacitor to reach full charge instantly, whereas in real life there would be internal resistance in the circuit that would prevent the capacitor from reaching full charge instantly.